So you will have exactly 15 minutes. And the first speaker is Suchetan Das from IIT Kanpur, who will talk about chaos under periodic drive. So please begin now.
Yeah, thanks, Roman. Am I audible?
Yes.
Yeah. Can you see my slides? Yeah. Okay.
Yes.
Okay. Thanks. So this talk is basically based on our current work with 𝗬𝗶𝗶𝗍 session, Arnab P, 𝗦𝗵𝗶𝗿𝗀 and some broad motivation of for our work. So we know what is OTOC. So OTOC, or outer primordial correlator, is basically a useful probe for quantum chaos. So it tells that the operator growth, or the commutator growth of two operators of W and V in some state, if it has an exponential growth, then it can be proved through OTOC, or the outer primordial correlator, or the decay of the OTOC, which is in this form. So the exponential growth in this way is characterized by the decay of OTOC, where this lambda is the Lyapunov exponent, and this V is the butterfly velocity, and T star is the scrambling time. So generically, this chaos is basically the both properties of theory and state, because the theorem is it is the property of the chaotic Hamiltonian also, and state means it is the property of also the state. Like for example, like large C 2D CFT in thermal state is chaotic, but if you consider the like minimal model in 2D CFT, and in thermal state it is not chaotic. Okay. So now one could ask another question is like that, which safety has holographic semi-classical bulk gravity description. So we already know that large C large gap safety 2 has this description, and recently after MSS bound, that maximally chaotic theories which saturate this bound, that's MSS bound, it has also the description of holographic semi-classical gravity. So now from these two facts, one can ask that do large C CFT2 is always chaotic or maximally chaotic? The answer is actually it depends. It is also, of course, chaotic in thermal state or in equilibrium, but it is not chaotic in vacuum. Like it has power law growth in OTOC in vacuum state. So this statement, the maximally chaotic theory is holographic, has holographic bulk dual. It is only in equilibriums, only in thermal equilibrium case. Now, so the question is that what about the chaos or the chaotic property in out of equilibrium scenario? Like one can ask, like, is last CFT2 is chaotic beyond thermal state, or can we have any notion of scrambling in an open system, or any bound of chaos in non-equilibrium system? And or what is the role of scrambling in a non-equilibrium system to reach equilibrium? Like what is the role of scrambling to reach in thermalization process? So all this question actually has some non-equilibrium setup, and and also this question may set important insights in black hole phase, like the formation or evaporation process of black holes. And also this question may put in important criteria on non-equilibrium system to have gravity dual. Now, to study these questions or this out of equilibrium question, we must go beyond the thermal state or time independent Hamiltonian dynamics in to compute OTOC. Like so, if we consider any out of equilibrium scenario, we must go beyond thermal state, and of course we must we can go beyond the static Hamiltonian dynamics in node if compared to OTOC. So one question is like, what is the scrambling notion of scrambling in quantum quench process, and or in particular in 2D large CFT, if can we consider any can we have any example of 2D large CFT is chaotic in any other non-trivial non-equilibrium state, like particle state in the context of quench, which actually mimic thermal state at last time. So for this type of question, you see the Arnab P talk today and afternoon. Now another question is that is the 2D large CFT is chaotic in vacuum state due to any non-trivial Hamiltonian dynamics, like we calculate OTOC in vacuum state, but due to the non-trivial Hamiltonian dynamics, is there any notion of chaos in large C 2D CFT? The answer is yes, and that is the part of my talk, and the answer is that for driven CFT which has no equilibrium analog. Okay, so let's go with the plan of my talk. So we in this talk I will discuss some key results of an ongoing work of computing OTOC driven to the safety. So plan of the talk is the following: that we first give a brief review of periodically driven safety, like the emergence of different phases, like heating phase, non-heating phase, etc., and the observables like entanglement entropy, total energy, and classical Lyapunov in different phases. Then we'll go to our setup of OTOC under periodic drive, and we'll see some unusual feature of cross ratio. Then we'll see the exponential growth in heating phase, and we also demarcate different phases like heating and non-heating phase using this OTOC. Also, since this drive actually impose a special inhomogeneity in the driven Hamiltonian, so this implies the butterfly velocity and scrambling time is also position dependent. So our slogan is that 2D safety actually drive how it drive OTOC scale. Okay. So first we'll briefly review the periodical driven safety. So we just start with some state or ground state or psi naught or some state, and we just drive it through the Hamiltonian H0 and H1. Suppose for this case, suppose for the simplest case. So here H1 we drive with the Hamiltonian H0 for the time interval tau naught, and we drive H1 for the time interval tau 1, and we follow this periodically up to n times. So it is a n driven system. So it can be written in this way, and it also generalized to arbitrary SL2 arbitrary U. I mean H1 is H0, H2, H3, and etc. etc. And here this n actually plays the role of the stroboscopic time, which is basically the time is here n into tau naught plus tau 1 for these cases. So now here the H0 is basically the safety Hamiltonian. This is and H1 is the driven Hamiltonian or the deformed Hamiltonian, and here is this factor is the special inhomogeneous factor, and it has also imposed a periodic boundary condition at 0 and L, and the important point is that this Hamiltonian can be written in terms of L0, L1, and L-1. I mean, all the SL2 generators in terms of SL2 generator. So in this case, this H0 and H1 actually define this SL2 drive. And this, in the Heisenberg picture, where you can consider the operator evolution of this driven system. So this in the Heisenberg picture, this operator evolution can be mapped as can be recast as an coordinate transformation from Z to Zn, where Zn is the Mobius transformation or some in this way. So this picture actually tells that Mobius, this simple setup tells that Mobius transformation actually dictates the operator evolution of driven safety. So all these discrete data can be generalized to continuum case, where the HT is the continuum Hamiltonian, the driven Hamiltonian. When F1 is 0 and Ft is 1, then it is the H0. But when F1 is 1 and we consider the Ft is this way, where F0 is the driving amplitude, and omega d is the driven drive frequency. And for this continuum case, one can also consider the this U. One can also construct this U, and in this following way, and similarly, like the discrete drive, one can also construct this n-driven U in terms of this transform matrix, which is the Mobius transformation. So we just let us briefly review the basic the result already know in the literature. So in the n-cycle drive, this Mn is a transform matrix, and so it contains 3 types of Mobius transformation, and it can be characterized these 3 Mobius transformation in terms of the trace of the transform matrix. And if it is greater than 2, this is called hyperbolic, and it is less than 2, then it's elliptic, and it is equal to 2, then it's called parabolic. And these 3 transformations actually characterize the different phases, like heating phase, non-heating phase, and phase transition line. So for example, for total energy, if we compute total energy in the driven system, then it has an exponential growth in n for heating phase, and it has a power law growth in phase transition and oscillator in non-heating phase. Similarly, similar structure exists for entanglement entropy, which has linear growth in n in heating phase and logarithmic growth in phase transition. And one can also define a classical Lyapunov, who actually tells the growth rate of this matrix Mn, this transform matrix Mn in n, So, and it is always greater than 0 for heating phase, and it is 0 for both non-heating and phase transition. So similar analysis can also hold for continuous drive case, where we can, when an useful parameter is alpha, and alpha is this way, which is a function of both drive amplitude and drive frequency, and et. And when alpha square is greater than 1, then it is called heating phase. Alpha square less than 1, it is non-heating phase, and alpha square equal to 1 is the phase transition. So now we'll come to our work. What is that so far we have only seen that the lower point function has been studied in driven safety, but here we'll consider the higher point function, 4-point function, 4-point OTOC in lastly 2D safety. So this is the setup here, the WV, and but W is at n and special at 0, and PS 0 and special position is x, and n plays the role of stroboscopic time. So the general strategy is to compute the Euclidean correlator, and then we have to analytically continue to real time. That is, here the stroboscopic time is nt. So nt goes to nt plus I epsilon I is the analytic continuation, and from this defined epsilon ordering actually dictates the different time ordering, that is time order and after time order correlators. So main object of analysis in this case is the cross ratio eta. So it has been shown that when eta greater than 1 for eta is greater than 1 for OTOC, and it is less than 1 for TOC, at least for safety case. Now, now in our driven safety setup, we have seen some unusual spatial structure in eta. So for example, for eta, when eta we have a certain point of x for which eta equal to 0, we'll call this a fixed point. So it is a fixed point of this drive for when eta equal to 0. And also we have found an range, this range for which eta is always less than 1. So in heating phase. So this means that in this case, we have same TOC and OTOC. So this means that the X has the range of 0 to L, but this portion of this range, it has always less than 1, but this portion of this range, but 0 to this, and this is the fixed point. So 0 to fixed point, we have eta is greater than 1 for OTOC and eta is less than 1 for TOC. So the key result of our is that, that for largely 2D safety, we get that we know that for largely 2D safety, eta greater than 1 is implies that we have an exponential growth in OTOC, and eta less than 1 gives the trivial time order correlator. So in our cases, we see that in heating phase we have the exponential growth with the chaotic growth of OTOC, and in non-heating phase we have that this OTOC is oscillatory, and in the phase transition line it is the power law growth of in time in n. But the theta and s is the parameter in the drive, and it is only true for this range of x. So these are also demonstrates that OTOC actually demonstrates different phase structures like this heating, non-heating, and phase transition. And also Lyapunov in this heating phase exactly matches with the classical Lyapunov we actually defined earlier. But the question, the classical notion does not distinguish chaotic and integrable theory like largely safety and minimal model. It does not. It is always chaotic in heating phase. It is always chaotic in classical notion. But in the quantum, from the OTOC perspective, we see that it is it has different behavior for minimal model and largely safety. So also we see that the important result is we see this chaos is only in vacuum state, and it has no equilibrium analog. And another feature is the scaling time is position dependent, and it is the feature of spatial inhomogeneity in the drive. And another result is the butterfly velocity, and here butterfly velocity is also position dependent. So this is the form of the butterfly velocity, and we see that the hello.
Time is almost up, so just yeah.
Oh, I have just one more slide. Okay, just stop there. So it has this structure, like it has both superluminal and subluminal velocity regime, and it has okay. And also we have other result, like since the spatial inhomogeneity actually breaks the translational invariance, so we can study also study this type of correlator which has different from which we get different result. Like we get the similar Lyapunov growth for different phases, but we have different fixed point for eta and different range of x for which eta greater than 1 in the OTOC. And we have also more intricate structure for butterfly velocity and etc. etc. So and we also generalize this for periodic drives, but the generalization we get is still same. And there's some future direction, like what is the bulk story, and what is the connection to horizon formation, and what is the operator growth in this language, and is there any new holographic criteria for automatic equivalence system from this, etc. etc. Thank you.
Okay, so thanks. So actually, we really have time for questions, but if anyone has a quick question, you can ask.
I ask one.
Yes,
Okay,
yes.
very quickly, yeah.
So for this 4-point function, you said that this was a 4-point function of a holographic CFT. So presumably you were using some block.
Yes, yes. There's a large CFT. There's 𝗵𝗶𝗶𝗶 block. I mean identity block.
Yes.
Yeah.
So what kind of block? Like, is it the heavy light block or?
Yes, heavy light block. It's heavy light.
So if you used like some the block of 4 light operators, do you still expect that this oscillatory or this exponential growth to still remain, or is it only for the heavy light block that you see?
Yeah, this is only for the heavy light, since we have an analytic expression, but for 4
yeah,
lights.
even for 4 lights, you also have an analytic expression. So do you know what happens in that case?
No, that I don't know actually, but yeah, yeah, that's a good question. But yeah, but it is purely for the, like the Robert Stanford case, that heavy light block. We only consider this. Yeah.